There are several dimensions to the different kinds of vulnerabilities, like logical, digital, and analog mixed. Logical attacks are the software-based attacks that target the hardware's logical functionality, including logic sequence attacks, which manipulates the sequence of logical operations to compromise the hardware's behavior. Logic side channel, which exploits the information leaked through the hardware's logical operations. Trojan insertion, which inserts malicious logic into the hardware's design. Fault injection, which intentionally introducing errors into the hardware's logical operations. The digital attacks target the physical properties of digital circuits, excluding logical attacks. This includes timing, power, and thermal-based attacks, exploiting the timing, power, and thermal characteristics of digital signals, and voltage, current, and temperature-based attacks. The analog and mixed signal attacks target the physical properties of analog and mixed signal circuits, excluding logical and digital attacks. For example, glitching, faulting, and RF attacks. So, what do? We begin with a digital design, for which Cadence maintains a comprehensive database. This database enables us to create extremely accurate models of the design, correlated to the manufacturing process, ensuring hardware accurate representations. There are various ways to model a design, and we utilize these models to identify potential vulnerabilities. For the software-based attacks, we use emulators that combine hardware and software to mimic real-world scenarios, allowing us to conduct software-based red teaming exercises to test the design's security. For the fault injection attacks, we employ fault simulators, which were developed in-house, to inject faults into the design and analyze its behavior. This technique is also used in the automotive industry to test failure resiliency. After simulating various attack scenarios, we perform statistical analysis on the design's power consumption patterns to identify potential side channels. This analysis is based on well-documented algorithms, which help us detect anomalies and vulnerabilities in the design. Generating attacks is challenging. When it comes to generating attacks, the complexity arises from the multitude of options that can be employed. The hardware testbench utilizes a custom-built hardware testbench to simulate attacks. You can employ a pseudo-random testbench to generate random stimuli for attack simulation. Using the prime mission equipment, you can leverage the actual hardware equipment used in the system to simulate attacks. Then, hardware debug entry points, JTAG, utilize JTAG, Joint Test Action Group interfaces, to access and manipulate the hardware. You can also use software and synthetic software approaches to mimic the behavior of the actual system. Use automatic test pattern generation, ATPG vectors, to create test patterns for attack simulation. Utilize formal properties to specify the desired behavior of the system and generate attacks that violate these properties. You can also employ speed bridge-connected hardware hacking tools to simulate attacks on the system. Each option presents its own challenges and complexities, making it difficult to generate effective attacks. Additionally, ensuring functional safety adds another layer of complexity to the attack generation process.